So I'm just going to do a very quick summary of complex numbers, with very much a focus on what you need to know for this course. So I think you're pretty familiar with the idea of the imaginary unit, square root -1, and then you can construct a whole bunch of complex numbers of the form a plus ib, and these are called the real and imaginary parts respectively. So that is, let I equal square root -1, and then you've got some complex number which we'll call z equals a plus ib, where a is called the real part, b is called the imaginary part of this complex number. And you can draw little pictures of them. So this is the real axis, it's the imaginary axis, and you got a, b there, right? That's all first year stuff. If you're still wondering about it, go back and revise Math 1.8. The key results that you need to know are this Cartesian or rectangular description's not that useful. Indeed, what usually happens is that we start using a polar form where you treat it with this angle and with some magnitude. That magnitude isn't usually called r, it's usually denoted the absolute value or the modulus of the complex number z. Now this polar form gives us the notion of these two bits. So this is the imaginary bit and this is the real bit. And with trigonometry we can deduce very quickly this representation of the complex number, where the real part a is equal to modulo z cosine theta, modulus z sine theta, plus the imaginary part, right, b, that's just the modulus of z, the complex number, this thing here, multiplied by sine theta. Okay, now if you want to figure out what the modulus of z happens to be, you can still get that out of the this Cartesian rectangular form. That is all right. So for any given complex number where you're given an a and a b, you can convert into this trigonometric form. That trig form gets written as like that, or sometimes this disgusting notation. So, right, where that CIS stands for cosine I and sine. The key result in complex numbers is that this form here is equivalent to an exponential form. That is, that z, the complex number z, can be written as this, and it can be written as that. Well, this is called the exponential form, and this is the form that we like to use because it is very easy to manipulate. Dealing with trigonometric functions is difficult because you always have to go and refer to trigonometric identities. If you want to raise cosine to a power, you've actually got to think about how that's going to work. If you want to raise an exponential to a power, you simply go ahead and raise the exponential to the power. Right? The sole reason this exponential form is used is because it is convenient to manipulate. The exponential form represents the underpinning complex number. You basically back it out, you figure out the real part and the imaginary part from the identity e to the I theta equals cosine theta plus I sine theta. The proof of this is by Taylor series. And you can look that up if you wish. It's quite a neat proof, but the proof is irrelevant here. What you need to remember is this is how we represent a complex number. So let's think about how we're going to use this in waves. So we use the trig functions sine and cosine to represent a wave. They're actually equivalent, so I could write sine or cosine. The reason is that a sine, right, like, ooh. I think if I make a scribble, it thinks that I'm erasing something. So here's the sine. The cosine is just a phase shifted sine. So if you shift the phase of the sine by pi on 2 or 90 degrees, you get a cosine. So this sine and cosine are equivalent, and you often represent a wave with an amplitude, a trig function, some sort of frequency. You might have a wave number in there, which is a sort of, if you like, a spatial frequency. So you can have a variation in both time and space, and you give it some sort of phase. Okay? Now, actually, I'm going to write cosine instead of sine. They are equivalent, but cosine means that is the real part of a complex number. So this wave could be represented as the real part, and I'm going to use this RE to mean take only the real part. In the textbook, let me just go and flip to it so I can do this properly. There is an extremely fancy looking R symbol used. So it's like got this curly thing like that. And you go up, this is thicker, it comes back down. And it's quite thin in there, so that's thicker, and then there's like lip. Right, that's your fancy looking R symbol that is used in the book to mean real part. You'll see that RE is a lot easier to write. People don't like it because it's confusing with Reynolds number, but honestly, context is sufficient to tell that apart in almost all cases. And the other thing you can do is you can do a drop, so you can kind of run the two together for the real part rather than the Reynolds number. So you can do a slightly cursive thing. So you would say that this is the real part of amplitude, the exponential, and then you've just got this argument. Frequency times time plus k times wave number times space plus phi, the phase, and that's it. Right, so now we have all of the tools that we would normally use to manipulate an exponential to be able to manipulate waves. So if we want to multiply two waves together, that corresponds to adding the arguments of the exponential, and that's really the power of the complex representation of a wave. So let's just say we've got two waves that only vary in time and there's no phase shift in place. They've just got different amplitudes. You multiply them together and you end up with this new wave that looks like this. Yeah, so what does that actually mean in practice? Well, you take the real part, and you see that you've got a wave with this new with the amplitudes multiplied and the frequencies added up. Right, so that just tells it just makes your life so much easier than having to multiply a couple of cosines together and looking up the appropriate identities. So that's a fast enough recap of complex numbers for our purposes.